Our task was to find the emergency evacuation times of the new library at the University of Birmingham. The library has 5 floors and each floor has a different layout and maximum occupancy. There are 3 final fire escapes in the building that are connected to stairways running along the edge of the building. In the event of an emergency, the lifts and the main stairs will be closed off, so these stairways would be the main means of evacuating the building.
So this is our initial model. We used it to work out how long it would take different groups of people to exit the room. So here D represents distance from the nearest group to the door. And so for example, it would take group 4D 1, 2, 3, 4 times D meters to get from where they are to the door. So our assumptions include that everyone travels at the same speed, that the same number of people go through the door at once, and each group follows the quickest way to get to the door, and they can't go diagonally because there are tables in the way, so they follow a non-diagonal route, and also all groups get up and start to move to the door at the same time. To expand this onto model 2, what we did is we took the room in this model to be a floor of the library, and each group of people to be a group of rooms.
The equation we're using to calculate the time it takes to leave the building is the maximum of x over v, which is distance over the speed that people are walking, and the time for the previous group to have left. And then from that we add on the number of people divided by the rate at which they're leaving to get the time for that group to leave. The maximum function we're using is explained as, say, the first group gets to the door and they'll be queuing to leave. Then the next group, when they get to the door, either they'll have all left and therefore they can carry on with no queuing, or this previous group will still not have left yet, which will be added onto their time to evacuate the building.
This image here shows a cross-sectional map of the library consisting of 6 floors. The green dots represent areas where there could possibly be queuing. For example, at this exit here, there would be queuing if when the first floor reaches the ground floor and there are still people from the ground floor exiting, there would be a queue would form. This happens for all the other floors and therefore contributes to the exit time of the library. We researched how long it takes to get down the stairs by timing 3 separate staircases and taking an average. From this data, we found out that the average time to walk downstairs is 26 seconds, which is then incorporated into our model to work out how long it would take, for example, the first floor to get to the ground floor is 26 seconds plus however long it takes for that room to reach the exit on that floor. If, after that time, the people on the ground floor have still not exited the building, there would be a queue of the ground floor. These are fire exits. The room here was ignored, as the time for this group to leave out this exit would have no effect on the overall evacuation time of the library. It can also be said for this door here, as there's no staircase leading down to this door. However, we had to model the rooms on the ground floor so they could affect the queuing time from other floors. However, we saw that each floor has 3 fire exits, A, B and C, which each a staircase leading down to the ground floor. From these, and looking at each room, we worked out which fire exit was nearest to each room. So for example, room 2 here, the nearest fire exit is straight up here to A. From the plans, which have distances on them, we worked out how far it was from each room, and using that we could work out the time for that group to reach the fire exit. We assumed that at each door there was no queuing here and that everyone was already at the door before leaving the room, and only queuing occurred at each fire exit individually.
We modelled our results on a spreadsheet. This is a very confusing process, therefore we only did 2 floors, the ground and the first floor, looking at each staircase A, B and C. From this, the results we concluded for both the ground and first floor was that at staircase A it would take 50 seconds for everyone to leave, at staircase B it would take 190 seconds for everyone to leave, and at staircase C it would take 232 seconds for everyone to leave. Therefore, from this we could see that staircase C is the rate determining step in the equation, and that 232 seconds is the answer for how long it would take everyone to evacuate from the ground floor and the first floor. We would then continue this modelling onto the second, third, fourth and fifth floor if we had time to continue this model.